Record. Good. Well, happy Monday. Today we cover the last topic in chapter 14, Lagrange multipliers. So we're going to be finding mins and maxes now with a constraint equation as well. This is the last topic that will be on our quiz 4. So that means quiz 4 will consist of 14.6, which is stuff about gradient vectors and directional derivatives, that sort of stuff. We have 14.7, which we had 2 class days over, that covered the local mins and maxes, and then also the absolute mins and maxes, right? So both of those days are fair game. And then today's stuff, this 14.8 Lagrange multipliers, which you've seen the pre-class video, but we'll do more examples in class, of course. Other than that, don't really have so much administrative announcements. I guess our midterm exam is, looming about, 10 days away or so. So it's next week, Thursday. That's going to consist of the chapter 14 stuff, which was the topics of quiz 3 and quiz 4 coming up. And then a bit of the chapter 16 stuff that we'll be doing between now and our midterm. So we'll have 3 sections or so from chapter 16, 16.1, 16.2, and 16.3, which will also be fair game for the midterm. So I've released the checklist or the topics that you maybe should go through, and certainly all the stuff from chapter 14. Now would be a good time to go through and just kind of see what are you happy with, what do you still need to study a bit more, and go through all of that. And I've also, just before class here, so I put the exam review document up on our D2L folder as well. So that'll be the topic of, just the Wednesday before the exam when we're doing some exam review. So you can take a look at that as you would like. All right. Don't think I have anything else administratively. Any questions before we jump into our math for today? All right, math it is then. So again, the topic for today is Lagrange multipliers. In the video before class, basically we had just one example that we used to try to motivate. And I showcased, kind of graphically what's going on here and why kind of this technique of Lagrange multipliers makes sense, that it should work. And so we had basically the topic was a real world-ish situation, right? Where we have a rectangular box, we have a certain amount of cardboard that we're using, and we'd like to maximize volume. So we want to find some maximum. The big thing here that we talked about is this bit about level curves. So we looked at the level curves for the volume equation, and then we also looked at the constraint equation. And I argued kind of geometrically that at this point where we just skim, right, this volume equals 4, that this is probably the, as good as we can do. And so the fact that these have parallel normal vectors was kind of the point of part C here. So we have these normal vectors that we can calculate out thanks to our gradient, the stuff from 14.6. And we use that to verify algebraically. And this involved solving a system of equations, and we will do more of that in class today, but that's what I find is usually the difficult part of this, is not taking the partial derivatives or anything too much calculus related, but it's really this algebra technique of how do we solve system of equations, because there's not kind of one universal method that you use every single time to solve every single possible system of equations. There's a couple of different techniques that we could use. Quite often we like to stick with substitution if possible, but there are different techniques that we can use to solve systems of equations, and so you kind of have to be a little bit careful, and you have to be a little bit clever and involve cases sometimes. And again, we're going to get more practice in today's class, but that part is usually the headache of this section. And so that inspired, again, this technique of Lagrange multipliers. And so ultimately, we're going to be setting up this system of equations where we're taking gradients and saying that they need to be parallel to one another, so they're just off by some scalar. We're going to use the Greek lambda, right, for Lagrange. I think Weberk uses capital L, just because we don't have a lambda button in our keyboards. And then also the constraint equation, solve that system of equations, 3 unknowns, and we should be able to find algebraically what the solution is. And then we don't need to necessarily have contour maps and all that sort of stuff for each problem. So that's the pre-class video in a nutshell. Any questions about this one before we move on and try to tackle some new problems for today? Okay, well then, why don't we go ahead and look at the new stuff. So I would like to use Lagrange multipliers to find a maximum and minimum for this function here, subject to the constraint that x times y should be equal to 1. And I've included on here some level curves and our constraint equation as well, just so that we can use this to hopefully verify that our answer is reasonable. But maybe we'll do this algebraically first and then use the graph at the end to kind of showcase visually what we have done. So again, for the technique of Lagrange multipliers, and this problem does start off by saying use Lagrange multipliers, we have two equations really that we're hoping to satisfy. So first is the gradient of f should be some scalar multiple of the gradient of g. And then we also have that our constraint equation, which should have some x's and y's, should be equal to some constant. So the first thing here, well, we have nicely named, I suppose, our function, which is x squared plus y squared. And so this other bit here, this x times y equals 1, is our constraint equation. So we're trying to find solutions to maximize and minimize this along this curve when x times y is equal to 1. So this bit right here is our x, y is equal to 1. So again, our constant is 1, and our g function, our constraint function, is x times y. So now we need to go ahead and calculate out our gradient, similarly to what we did in 14.6. So I'm going to calculate out my gradient of f. So the first thing in the gradient is always supposed to be our x derivative. So I'm going to have 2x. And then the second thing is going to be our y derivative. So I'm going to have 2y. So that's my gradient of f. So again, f sub x is always in the first bit. F sub y is always in the second bit. Next up, we're going to have some scalar. So an unknown scalar for the time being. You could use A or B or C or things like this, right? To just say it's some unknown scalar. But again, because this is the Lagrange multipliers, typically we use this Greek lambda. And then finally, we need to have our gradient of g. So our g function is this x times y. So if I take the partial derivative with respect to x, I'm going to have y. And if I take a partial derivative with respect to y, I'm going to have x. So these right here should give me 3 equations and 3 unknowns, and then my goal is to solve that system of equations. So let's write these down, what they are. The first is when we take these vectors and we want all of the x components to be the same, right? They should be equal. So on the left-hand side, I have 2x, and on the right-hand side, I have lambda y. Because again, you would kind of do scalar multiplication through by this scalar lambda. And so you'd have lambda y in your first component. Oh, sorry, yes, question. So it's because I took a partial derivative, and this was my function that I took partial derivative of. So when I took a partial derivative up with respect to x, I got 1 times y. And then likewise, when I took a partial derivative with respect to y, I had x times 1. My second equation is that I'd like my second components to be the same, right? Or my y components. So this would be 2y is equal to lambda x. And then finally, I have x times y should be equal to 1. So these are my 3 equations, and my 3 unknowns are x's, y's, and lambdas. And this is what I want to solve to try to find, hopefully, mins and maxes, right? So again, when we're trying to solve these things, this is where kind of you have many options at this point. There's not a unique correct way to go about solving this every single time. So with this system here, I may be tempted to say something along the lines that, x is equal to lambda divided by 2 times y. So I'm just taking my first equation and solving it for one of my variables. This is a common technique, because then once we have one of our variables solved for, we can substitute that into another equation. So I'm going to go ahead and substitute that in to my second equation. And what I'm going to have is 2y is equal to lambda times x. And instead of x, I'm going to substitute and put lambda over 2y. So I'm going to go ahead and rearrange a little bit here, and I'm going to write this as 4y is equal to lambda squared y. This is where we have to start being careful. This is where, like we saw last time when we were solving some system of equations to find critical points and whatnot, I said you have to be careful about canceling, right? Because I'm tempted right now to divide by y. But if I divide by y, that's assuming something, right? It's assuming that y is not equal to 0. If y is equal to 0, right, then this is already satisfied. This is true, right? So I need to consider almost two cases here. So if y is equal to 0, and then I'm going to consider if y is not equal to 0. So first of all, if y is equal to 0, what happens, right? Well, first of all, this equation now says that 0 is equal to 0, so this is satisfied. This is true. However, when I go and I look at my third equation down here, I need to choose an x value to make sure that I'm on my restraint equation, right? So I have x times y is equal to 1, which is gonna, if y is equal to 0, this says that 0 has to be equal to 1. And that's a problem, right? And so this tells you right here that there are no solutions to the situation when y is equal to 0. We considered it, right? But it turns out the constraint equation says that this is impossible. You can't have y is equal to 0. And in fact, if we look at our picture here, our constraint equation is in red. And notice that when y is equal to 0, when we're on the x-axis, right, that's an asymptote. So, right, we actually never cross on the red equation y equals 0. All right, so now if y is equal to 0, sorry, if y is not equal to 0, then we can go ahead and, like my instinct was leading me, right, I have 4y is equal to lambda squared y up here. I wanted to cancel the y's. And so long as y is not equal to 0, I'm allowed to do that. So then I'd have 4 is equal to lambda squared, which means that lambda is equal to plus or minus 2. Okay, so if lambda is equal to plus or minus 2, right, can I figure out then what y and x must be? So again, we kind of see that there's going to be a few cases. So I'm going to go ahead. It's almost like I'm writing a program or something now, right? If lambda is equal to 2, my question is, what happens? And then if lambda is equal to negative 2, what happens? What are the solutions in that case? All right. So if lambda is equal to 2, then I could look at really either one of these first or second equations, and we're going to get that y is equal to x. Plugging that into my third equation, which says that x times y has to be equal to 1, and just doing some substitution here, that's going to tell me that either I could write x squared is equal to 1 or y squared is equal to 1. So this tells me that x is going to be equal to plus or minus 1, which tells me that I have 2 points, right? I have either 1, 1 is going to be a potential min or max, and then I have negative 1, negative 1. Because again, in this situation, when lambda was equal to 2, we knew that y was equal to x. So whatever x is, whether it's positive 1 or negative 1, y has to be equal to it. So these are 2 possible mins and maxes. The final case is if lambda is equal to negative 2. So if lambda is equal to negative 2, then I'm going to have the situation, again, kind of going back up here, I can look at really either my first or my second in my system of equations, and I'm going to have that y is equal to negative x. When I plug those into my third equation, that's going to give me something along the lines, right? It was x times y is equal to 1. Let's go ahead and substitute in, and instead of a y there, let me put a negative x. So this tells me that x squared should be equal to negative 1 if I transfer that negative to the other side. And luckily, right, again, we don't have complex solutions in our class. We're not doing complex calculus. We're only doing real valued calculus. So, I mean, I or negative I would be the solutions, but those are complex numbers. So there are no real solutions in this case. I'll just put a little frowny face. Reality, I'm happy because kind of having fewer options for solutions is not a bad thing. So it looks like the only points when I'm solving this system of equations, the only real solutions that I have to this system of equations are when lambda is equal to 2. And in that case, we have that the points 1, 1 and negative 1, negative 1 come out as possible solutions. Let me go ahead and showcase here some normal vectors. So at 1, 1, maybe a normal vector would look something like this for our constraint equation, right? It'd be perpendicular to the curve. And at negative 1, negative 1, we'd have some normal vector perpendicular to the curve. And notice that in this particular case, I didn't draw the level curve, part of the contour map that would include this, but we know that there's some value here where the height would be, again, some circle centered at the origin, and that the normal curves for this would again be perpendicular. So they're just some scalar multiple off. They're parallel to one another. So these are the solutions to the Lagrange multiplier setup here, but still we need to classify these things as maximums and minimums, right? So let's go ahead back to my F equation. So I have f of 1, 1. And I have f of negative 1, negative 1. Again, my function was x squared plus y squared. So when I plug these things in, 1 squared plus 1 squared, that's 2. And when I plug in negative 1 and I square it, or in negative 1 and I square it, I still get 2. So my final question here is 2 a maximum? A minimum? Is it both? What's going on here? How do I know if it's a maximum or a minimum, or what is 2 in this case? Anyone have a guess? Guess? You're guessing maximum. Any reason why you like maximum over minimum? All right, you have a lucky coin, and that was your flip. Sure. And that's fine for a guess. So what if we were to choose another test point that's on this curve, right? Suppose I chose, no, not quite there. So if I chose when x was equal to 1. So again, oh no, sorry, that was, I have 1 there. Let me do 1/2. So x is equal to 1/2. Got confused by my scale. So if x is equal to 1/2 and I'm on my constraint equation, which again is x times y must be equal to 1, can someone tell me what y is equal to? 2, right? So the point here is 1/2, 2, which makes sense from this graph. Let's go ahead and plug that in. So if I plugged in 1/2 everywhere I saw an x and a 2 everywhere I saw a y, again, I'm supposed to have x squared plus y squared. So it's going to be 1/4 plus 4. So that's going to be 4.25. So I'm no longer happy with your answer of 2 as a maximum, right? Because we were able to achieve larger than 2. We were able to get 4.25, right? So it turns out that both of these here are minimums. But this is not obvious, and it requires a little bit of thinking as far as is this a maximum or a minimum? So for instance, one thing we can think about is for x squared plus y squared, the smallest value possible would be 0, right? That would be the absolute minimum for this thing if we weren't on this constraint equation. And if you want to get those small values, you want to be plugging in things that are close to the origin, right? So for instance, if I plugged in 0, 0, that would be how I achieve 0 for my range. But notice that I can't actually get that close here. On the other hand, for maximums, I just need to go kind of as far away from the origin as possible. So I could even go something like way up here. For instance, if I did like x equals 1,000, and then y was equal to 1/1000th. And if I plug that into my function, right, again, I have to take my x and square it, and I have to take my y and square it, and then add those results. Y is quite close to 0 in that case, right? If you take 1,000th and you square it, it's going to be like 1/1,000,000th. And on the other hand, when you take 1,000 and square it, if you take your x value and square it, you're going to get like 1,000,000. So it's right, it's going to be 1,000,000 and a little bit of change. So you can get as kind of as large as you want here, but it turns out your minimum is going to be the 2. So all this to say, Lagrange multipliers can only find minimums and maximums if they exist. We did not start 14.8 with an extreme value theorem, right? The extreme value theorem guarantees when we have an absolute minimum and an absolute maximum, right? This turns out to be a closed set. If we look at our set of points that satisfy our constraint equation, it does include all of its boundary points, but and so it is closed, but it's not bounded. So the fact that you can go off to infinity in either direction, right, is the fact that there may not be a minimum or a maximum. In this case, it turns out there's not a maximum, but there is a minimum. All right, so this would be the final answer. The absolute minimum here is 2. There is no maximum. So no maximum. Oops. No max. All right, questions. One right here, yes. How do I know it's not a saddle point? So the technique for Lagrange multipliers is different than, finding critical points and all this sort of stuff. We never took a derivative and found when it was equal to 0, right? So again, kind of a little bit back on the pre-class video, that this is not like if we were to consider this without the constraint equation, this would not be a critical point whatsoever. So it doesn't really make sense to say, well, it's a local min or a local max or a saddle point sort of deal. It's probably not a critical point whatsoever. And so, yeah, we use a completely different technique for them. Does that kind of make sense? Good, yes.
Doesn't every function have to have a maximum, or is it just infinity?
So yeah, it's if you talked about like the limit or something like this, then you could say the limit would go off to infinity, right? But yeah, any real number that you tell me, like if I say that the maximum is 3 billion, right? You can go out and find an XY pair that satisfies the constraint equation for which the function's value is larger than 3 billion. And then someone else could come along and say, well, no, it's actually 5 billion, right? And you could find an XY pair, right? So no matter what real number you write down, you're wrong. And in that regard, there is no maximum. There's no real valued maximum, right? If you say, well, it's infinity, that's kind of, it's not a real number, right? So that, but yeah, the limit would go off to infinity. All right, good. Well, why don't we go ahead and try another one here. Use Lagrange multipliers to find the extreme values for this function on the circle, x squared plus y squared equals 1. This one, the constraint equation is a circle of radius 1. So this will be closed and bounded. We will be able to find mins and maxes for this. So that's going to be nice. Let's set up our system of equations, and then maybe I'll give you a couple minutes to try to solve the system of equations, because that, I think, is the most difficult bit. So again, we're going to be doing partial derivatives, or gradient of f is equal to some scalar multiple times the gradient of g. And then our constraint equation is x squared plus y squared is equal to 1. This one right here, if I was to take my gradient of f, I would have 2x. And in my second component, I'm going to have 4y. This should be equal to lambda. times the gradient of g. So again, I'm going to have 2x and 2y. So my system of equations is that 2x is equal to lambda times 2x. I have 4y is equal to lambda times 2y. And then I have x squared plus y squared is equal to 1. So these right here are my three equations with my three unknowns. And again, I'd like to give you maybe 2 minutes or so to please try to solve this system of equations. And again, with this one, just like the last one, there will be some cases that you need to consider, right? What if something is equal to 0? What if something's not 0? All that sort of stuff. So please don't forget your cases. Another 30 seconds or so. Get as far as you can. All right. Well, kind of quite similar to our last situation, our last problem. I see this setup where I'm immediately, tempted to cancel out x, right? And so you can cancel an x so long as it's not 0. And so I'd like to go ahead and start off by then making some cases. What happens if x is equal to 0? And then what happens if x is not equal to 0? Because again, I want to cancel that x, but I can't do that all the time, right? So if x happened to be equal to 0, this first equation would just say 0 equals 0. So I don't get a lot of information from that. The second equation, and I could simplify it a little bit, but it'd say like 2y is equal to lambda y. And again, we're being careful about canceling. I'm not sure if y is 0 or not yet, so I'm holding off for the time being. My third equation would say, right, again, if x is equal to 0, that y squared should be equal to 1. Right, because it's originally was x squared plus y squared equals 1, but again, x is 0 in this case. So this is going to tell me then that y is going to be equal to plus or minus 1, which means that I have a few subcases, right? So the first subcase is if y is equal to 1, what happens? Well, that's going to tell me if y is equal to 1, then I'm going to have 2 is equal to lambda. And again, that's me plugging this into my second equation. And lastly, if y is equal to -1, let's see, again, these would cancel out and I would get that 2 is equal to lambda. So I get from this situation, this case, when x is equal to 0, I get the points 0, 1, and 0, -1. And these both occur, they have a lambda value of 2. So the scalar multiple, they would be off by a factor of 2. Okay, so there are two solutions to my system of equations. The next case is when x is not equal to 0. And in this case, kind of my whole motivation was, can I cancel x or not, right? And so my first equation, if I can cancel x, would say that 1 is equal to lambda, right? So again, I'm looking at my first equation up here, canceling the x, and I'm canceling the 2 as well, right? And so on the left-hand side, I have 1 left, and on the right-hand side, I have lambda left, right? So now at this point, I'm going to have what my second equation would say that 4y is equal to 2y. And my third equation would say x squared plus y squared is equal to 1. Now, it's pretty hard to make 4y equal to 2y, right? The only way that this really happens is if y was equal to 0, right? Otherwise, if y is not equal to 0, then these would cancel, and you just get 4 equals 2, and now you have a nonsense answer, right? There's no way that you can make 4 equal to 2. So this is going to imply then that y has to be equal to 0. Otherwise, the second equation is not satisfied. So if y is equal to 0, now plugging this into my third equation, I'm going to have that x squared is equal to 1. So if x is not equal to 0, then x is going to be plus or minus 1. And again, all of this happens where we have a lambda value of 1, turns out. So we have the 2 points here, 1, 0, and -1, 0. So usually for solutions for Lagrange multipliers and whatnot, you usually like to categorize them by lambda value. So I would say, if lambda is equal to 1, then we have solutions 1, 0, and -1, 0. And if lambda is equal to 2, then we have potential solutions 0, 1, and 0, -1. Question?
To verify the -1, 0 solution. Work with the 2x equal 1 to 2.
Sorry, one more time. 2x. So if we were to go ahead and plug this back in, -1 is equal to lambda to -1 here. Then the -1s would cancel, and the 2's would cancel, and lambda would still be equal to 1. So the fact that there's x's on both sides makes this true. But it's never a bad thing to go back and double check in the original equations. Sometimes this can help you catch a small mistake. All right, so now we need to find minimums and maximums here. So if I go ahead and plug in all of these values, -1, 0, and f of 0, -1. And we're plugging this, our function is x squared plus 2y squared. So x squared plus 2y squared. So we have 2, we have 1, another 2, and another 1. So again, our constraint equation in this case is this circle of radius 1. This is a closed set. It contains all of its boundary points, and it's a bounded set. And so we are going to have our minimums and maximums achieved at least once, thanks to the extreme value theorem. So that's how we know with certainty that 1 here is going to be our absolute minimum, and 2 is going to be our absolute maximum. And you could try to plug in other values and whatnot, but again, you're not going to get any better than 1 for your minimum and 2 for your maximum. Question, yeah. One more time. So yeah, if you wanted to start off with a different assumption, like y is equal to 0 versus when it is not equal to 0, you would come up with the same solutions, right? So, and that's a completely reasonable way to go, right? I just took my first equation here and I got tempted by canceling x, right? And so that's kind of what led me down this path of when can I cancel x versus when can I not, right? But you could have looked at the second equation for whatever reason, right? And decided to look at that one and say, well, when can I cancel my y versus when can I not cancel my y, right? And you would have ended up with the same sort of path here. We turned out when x is not 0, y has to be equal to 0. So those kind of are friends, right? You would end up with a slightly different assumption first. You'd say, well, when y is equal to 0, you'd find that x can't be 0, and you would end up with a situation where lambda is equal to 1. And then in the other case, when y is not equal to 0, you would find out that x has to be 0. So either way, we get the same results, though. Yes? Yeah, so the extreme value theorem, let's go ahead back here. This came up in 14.7. It talks about when do you have to have both minimums and maximums, right? And it's when your region is going to be bounded and it's closed. So closed means that it contains all of its boundary points. No, it's a little bit confusing. But basically when you draw it, right, you're not using any dashed lines, right? And so quite often we drew a picture like this. So it needs to include all of its boundary points. So you need to draw it with solid lines. And it can't go on forever, essentially. So the bounded bit means that it's contained with some disk. You can draw a circle around it and you can get the entire region. And so now in this case, our set is this circle here, when x squared plus y squared is equal to 1. So first of all, when I draw this circle, I don't have to use any dashed lines. So it's going to contain all of its boundary points. And so it's a closed set. And also, I can trap it in a circle, right? It doesn't go on towards infinity in any direction. And so therefore, I know the minimums and the maximums are going to be achieved. In the previous situation, it is closed in that it contains all of its boundary points. When I drew my constraint equation, right, we didn't have to use any dashed lines. However, it goes off to infinity in multiple different directions. And so it's not going to be bounded. It goes off to infinity towards the negative y direction, towards the negative x direction, towards the positive x direction, and the positive y direction, right? It goes off to infinity in many directions. And so that's why it's not necessary that minimums, maximums are achieved on that set. Good. Any other questions? Right. Well, I have, I think, one more example for us. This is using Lagrange multipliers now in a higher dimensional case. So I have my function now with x's, y's, and z's in it. And I have my constraint equation now with x's, y's, and z's in it. And my claim is that the same technique will work, except for now we're going to have 4 equations and 4 unknowns. So it's going to be a little bit more painful. The textbook also goes into another situation where you have like multiple constraint equations as well. And so there are other variations that are not included in our curriculum at MSU, but this one is, and you will see at least a web work problem or two about it. So let's talk about this one. Again, we're going to set up the equation where our normal vector is going to be some scalar multiple of the normal vector for our constraint equation. And we're going to have our constraint equation itself. So in this case, the x squared plus y squared plus z squared should be equal to 9. Now, this is a sphere of radius 3. This is going to be closed and bounded. And so the extreme value theorem applies, and we are going to be able to find minimums and maximums in this case. So that's going to be nice. Let's go ahead and set up and take our partial derivatives. So for finding the gradient of f, we're going to have what? 2, 2, 1. So this was me taking a partial derivative with respect to x first for my function, then with respect to y, then with respect to z. This should be some scalar multiple of when I take my gradient, my partial derivatives, for my constraint equation. So when I do that, what I'm going to get 2x, 2y, 2z. So again, my g function over here is x squared plus y squared plus z squared. So let's go ahead and write down all of our system of equations that we have. So I should have that 2 is equal to lambda 2x. I have that 2 is equal to lambda 2y. And I have that 1 is equal to lambda 2z. And then finally, I have my constraint equation, x squared plus y squared plus z squared ought to equal 9. So this is my setup, my system of equations. Notice that I have 4 unknowns. I don't know what x is, I don't know what y is, I don't know what z is, and I don't know what lambda is. But luckily, I have 4 equations to try to help me solve this. Now for these ones, notice that if you try to set anything equal to 0, right? If I consider, well, what happens if x is equal to 0? Or what happens if y is equal to 0? Or what happens if z is 0? Or lambda is 0, right? Notice that once I set anything equal to 0, I get a nonsense equation from these first 3. So I am guaranteed that nothing's equal to 0 in this case, right? For instance, if x was equal to 0, if I tried to figure out what happens if x is equal to 0, this would tell me that 2 has to equal 0. And so already I know there aren't any solutions in that case. So therefore, x is not 0. So using the same method that we used last time where we tried to figure out, right, I don't see the same temptation here to try to cancel anything. And so we're not really led into this scenario of when is it 0 versus when is it not 0. And that's what I was getting on about, at the beginning of class when I was saying that kind of the system of equations, they sometimes feel a bit different. And so you have to use different strategies sometimes. So in this case, when I'm looking at this, I notice that I can pretty easily solve for x, for y, and for z. And so if I did that, and I was to try to solve for x, for y, for z, in this first case, I'd have x is equal to 1 divided by lambda. In my second case, I would have y is equal to 1 divided by lambda. And then finally, in my third case, I'd have that z is equal to 1 divided by 2 lambda. Again, essentially what I'm setting up here is a big substitution method. By solving all of these in terms of lambda, pretty easily here, I can then take these and I can substitute them into my final equation. And then I'll have an equation that just has lambdas in it. So I'll be able to solve for what lambda has to be. So if I take all 3 of these and I plug them into my final equation, I would have that instead of x squared, I'm going to have 1 over lambda squared. Instead of y squared, I'm going to have 1 over lambda squared. And instead of z squared, I'm going to have 1 over 2 lambda quantity squared. That these should sum up to 9. So with this, I'm hopeful that I should be able to solve now for lambda. So let's go ahead and take this just a little bit carefully here. So I'm going to rewrite this 1 over lambda squared, 1 over lambda squared, plus 1 over 4 lambda squared. Let's get a common denominator. I'm going to multiply here by 4 on top and bottom, and again here on top and bottom still by 4. So that way my common denominator is going to be 4 lambda squared. So now in my bottom here, 4 lambda squared. And in my top, I'm going to have 4 plus 4 plus 1. So I'm going to have 9. So that's pretty convenient. Now I can cancel these out. And so I'm going to be left with lambda squared is equal to 1/4. And so finally, I'm going to have lambda is going to be plus or minus 1/2. Now that I know what lambda is, I can break up into cases. So, right, what happens if lambda is equal to positive 1/2? And what happens if lambda is equal to negative 1/2? And I can plug those into my situation, right, my previous equations. So for instance, my first equation, if lambda is equal to 1/2, it would say that 2 is equal to 1/2 times 2 times x. Right, again, just plugging in everywhere I see lambda 1/2. And I'm looking at my first 3 equations up here now, right? So in this case, I just get that x is equal to 2. And likewise, if I plug in lambda equals 1/2, I'm going to get that y is equal to 2. Oops. And then finally, if I plug in lambda equals 1/2, I'm going to get z is equal to 1. So when lambda is equal to 1/2, it looks like I have a point that satisfies the system of equations, and that's 2, 2, 1. So that's the first case. And in the second case, if lambda is equal to negative 1/2, again, plugging these things in here maybe a little bit faster now. I hope that you'll agree with me that we're going to have just the opposites, right? So we're going to have x is equal to negative 2, y is equal to negative 2, and z is equal to negative 1. So we're going to have negative 2, negative 2, negative 1. Bless you. All right, so the last thing is, these are our points of interest. What happens when we plug them into our function equation? And so our function, let me just write it down here again so I'm not scrolling back and forth a bunch. 2x plus 2y plus z. So when I plug in 2, 2, 1, I'm going to have 4 plus 4 plus 1 is going to be 9. And when I plug in negative 2, negative 2, negative 1, I'm going to have negative 4 minus 1 should be negative 9. So our maximum in this case is 9, and our minimum is going to be negative 9. All right, any questions on this one here? All right, well, I'll stick around if there are any one-on-one questions. Otherwise, I hope you have a good rest of your day. Start your web work problems early. Again, the system of equations, they take a bit of time, and each one feels a little bit special. So you got to spend some time with it and figure out how are you going to attack this so that you can actually get solutions. So, all right, I'll see you Wednesday.